Good evening, everybody. This is Obi-Wan Pez for Simplex Pachinko. So, Super Brain. Starting us off early tonight. So, uh, slight variation on Mastermind might be interesting or might be trivial. That's pretty much how math boils down most of the time, anyway. Alright, let's hear it. Hi to everybody else who might begin. Let's see. Yeah. Might have somebody else in here. Yeah, okay. Let's turn the music down just slightly here. Okay, so speed run it. Is this for Fallout? Or no, you've been doing... Yeah, so Fallout has its own, yeah, Operation Tango, okay. Fallout has its own version of basically what you're talking about, but there's just a gigantic list of symbols, and hidden in the symbols is a series of words, and you're only selecting certain words. So you go over and you click it, and then it tells you how many are correct. And then, you know, you go and figure out what other words are going to make that match. I don't know if it tells you how many are correct and how many are in the right location. I think it's just how many are correct at all. And it's, I mean, you only got like 8 words, but you have 4 guesses. So, unless you do the hacking thing, where you find a series of symbols that are all next to each other and form a bracket, and if you click that bracket set, it can do one of like 5 things. The main 2 are it'll refresh all of your attempts, and it will take out words that are false. So if you do like 2 guesses and they're false, you might want to start looking for brackets instead to either refill or eliminate other words. Anyway. Okay. So you could, for instance, have 4 correct, but they're incorrectly placed. And it's binary, so that's nice. Oh, okay. And in that case, you can only have 2, 3, or 4 in the incorrect positions, because either it's got to be 2 that switch, or 3 that are in a rotation, or 4 that are in some combination of either swaps or rotations. So that could be interesting. So if you're doing a 4... I don't know. Yep, okay. Yeah. So again, you guess 1, 0, 0, 0, and correct. Correct. 0, 1, 1, 0. So here, correct. 23. All right. So if we were to say then, like 1, 1, 0, 0, this would be correct to be 4, but incorrectly placed here would be well, 2 correct and 2 incorrect, but either way. Something like this. That could be fun. Well, at least that in that case you've got it correct essentially. You just need to invert everything. So okay, what's your new layer? Hmm. Huh. Do you know like um well that makes it a little bit weird. Uh, I wouldn't want to guess them anyway, given that at least not for the first couple of guesses, due to the fact that the distribution of ones and zeros follows the binomial distribution yet again. So thank you for bringing this to my channel because it exactly what we always do in this channel. Yeah, so the problem that we uh-huh. That makes it a little weird, yeah. So does it not give the person how many are correct on the first two guesses then? That would be rather a strange thing if it said like, oh, well the first one's got 3 correct. then it must know what the code is, in theory. Or have like a way to generate it specifically. Is that going to be deterministic? Like, is it always going to be 1 then 2, or is it just going to pick a random number on the first one and then generate all possible codes for the second one? And then whatever the person guesses, it's just going to pick one that's not the one they guess? Okay, so hint 1 is going to be random. Oh, on the first two. So, I mean, technically it's a 1 out of 16 chance, right? So this is to the fourth. So let's see. The chance of you not getting the code is going to be 15 16th. 16th. And if you said you were doing this, let's say even just to the 20th. Okay. So if we do 20 runs, you have a 27% chance, give or take, of never getting the code on the first try. In 50, that drops down to 4%. So possible, not very likely. And again, the first one is essentially random. So as long as the code is done, as long as the code is like generated randomly, let's assume for the moment that it's generated ahead of time because that's the more, I guess, reasonable. Um, okay. Right. So if we just assume the easy case, right? Assume the easy thing. They generate a static code every single time you go to the door. So it's different every time. You know, it is possibly different every time. It's selected at random before you get to the door, like, or when it when you approach it or when you first activate it. When you first press the keypad, it'll generate the code or something, whatever. That's the easy thing to do. Um, so if that's possible, again, you get 1 out of 16 codes. So you get a 1 in 16 chance to just walk up and press the right number, which, again, it's not terribly unlikely, but also not tremendously likely on just your first chance. That's 6.25%. So, all right. So 6.25% chance to just get it first try. So on the variation, there is a 0% chance of getting it on first or second. This is the mean variation. All right, man, I got like freaking notifications. That's not what I want. I want that one. All right. Let's just close this because okay. Oy. Mazaide, good evening. How's it going? Okay, so if you guess that it's just all zeros to get the number of ones that exist in the code, that makes sense, right? Especially since it's just binary. It's not like, a 9 or 10 digit code where you got 0 through 9, because that would be a nightmare. Um, so yeah, if we assume it's just the standard one, then 0, 0, 0, 0, we get the number of ones and also zeros because it's right, it's binary. So all right, so all zeros just get to the number of ones and zeros. So that is a reasonable thing to do, at least at first. Just say, okay, this is what I'm going to get. If you went with, let's see, any combination of 1 verse 3 or 3 verse 1, whichever way you want to go about that, this is going to be 1 choose 4. And so this is going to be 4 different possible combinations. If you do 2 verse 2, then this is going to be 2 choose 4, and you get 6 different combinations, and likewise back the other way down. So then this is 0 verse 4 is going to be 0 I'm doing this all backwards. Hey. So, 4 choose 0, 4 choose 1, 4 choose 2. 4 choose 1 is equivalent to 4 choose 3. And 4 choose 0 is equivalent to 4 choose 4. One of them. Okay. I keep like, it's weird. I hope I'm not cutting out at all, but it seems like it's just continually connected with the Bluetooth and it's not a problem. Right. So the only thing I was thinking was if you end up getting 4, right? If you nail it. Okay. So if you nail it exactly on the nose, any of these, then, obviously, if you just do the all 4 are the same thing, like all 4 zeros, you get a 1 in 16 chance, but you get the code automatically. If you get either you got 1 or 3 correct, there are 4 different combinations for that. And again, if it says that yes, all 4 of them are correct, then you have, again, those 4 different combinations to trade them around. Um, and if there are 2 and 2, you got 6 different combinations, which again. I'm trying to think if you're on 2v2, right? 2 of each, and you get a notification that there are 3 correct, then that means that just one of them is incorrect, which means that if it's a 1, there have to be 3 of one and 1 of the other. Right, okay. So you have to go from 2 and 2 to 1 and 3 if you have 3 correct. So that's just like a walk, basically. I think the same is going to be generally true for all the rest of them, right? So if you got 3 correct, then you're going to go from... Hey, Megalomor. It's a binary version of Mastermind. So, Superbrain plays Operation Tango, and was trying to figure out where the... trying to figure out the easy way to speed run this. Yeah, I don't know what's going on. Because, like, the receiver's right here. Yeah, so I get sort of a crackly sound because I'm also listening to the music. And then it goes beep boop, and I always worry that it's cutting out or something, but I think it's just reconnecting in that fraction of a second. But weird. I don't know why it's having trouble. It's not that old. Okay. So anyway, this is the yeah. This is the general case of just the simple version. And uh, so, right, Megalomorph, Superbrain said, now what if, just supposing here, the first two guesses are never correct? Like, no matter what happens, it's deterministic that you are not correct. And so, if that were the case, right, first and second guesses will be 0% chance to get correct. And then, hint number one is going to be completely random, but it's not the thing you picked. So it can be anything else that you want, or anything else that the developers want. Now I said doing the other way over here, where you just happen to be wrong all the time, is the easier thing to do, is far less code intensive, but let's just suppose that this is possible. So if this is the case, hint number one's just going to be completely random as long as it's not the code you pick. So your number of correct can either be 0, 1, 2, or 3. It can never be 4. So code just picks a random number, 0, 1, 2, 3. Although I guess that wouldn't be 0 if it was... Well, okay. If it was just 0, then you just invert all the numbers and you're fine. Oh dear. We've all got one of them, don't we? Okay, yeah. So if we just assume that this is also a binomial distribution, so you're going to pick essentially out of the 16 cases, and again, never... Okay, so 14 cases. You're never going to pick all correct. Oops, 4 choose 4, all correct. You're never going to pick 4 choose 0, all incorrect, because it's too easy. So these three, 4 choose 1, 4 choose 2, 4 choose 3, are going to be distributed as they are. So this is just a supposition. But if we assume that this is going to be the way it goes, then there's going to be 1 is going to be 4 out of 14. 2 is going to be 6 out of 14. And 3 will be 4 out of 14 again. Are you saying that it could also potentially be 4? Or you don't want that, right? Okay. But you will allow something like, 1000 has 4 correct, but some in the wrong position? Or do you not want that as the first hint? Okay. Or anything else for that matter. Alright. So hint number 2, if it's going to be in this mean sort of thing, then what's going to happen is... Actually, that's not going to be correct, is it? Because it's not actually saying... Yeah. So it's not going to be this distribution either, because if you guess 1000, it's not going to distribute them like this. It's just never going to be 0, and it's never going to be 4, I think is what you're going for. I mean, if you guess 1000 and you got 0 correct, then that's a big problem, because that means something's wrong in the code. That's not necessarily going to be this. Right. It is going to matter what it is, because we're assuming that we're wrong. All right. So it's going to generate all possible codes for, given hint 1. And then for hint 2, eliminate the guessed code. And randomly select another. And then output. Number correct. If 4. Number incorrect position. If you're at 0, 1, 2, 3, or 4, the number correct. It's going to toss 0. It's going to toss 4. Because 0 is almost impossible, and then it'd just be ridiculous if you had 0, 0, 0, 0 as your guess, and 0 was given as the number of correct. So that's not a particularly interesting problem. You just invert the code, and voila, you're done. If correct, regenerate. Code. Or it's not even correct, right? If number correct is equal to 0 or 4, regenerate. Hint 2. correct is either equal to 0 or 4. Regenerate within constraint of hint 1. Man, what a jerk. Okay, so yeah, that might be a little easier than to try to figure out this other thing. Yeah. So I put the output of H1 and H2 after the relevant regeneration, if possible, or if necessary in these particular things. What's the best strategy to find it quickly? Oh boy. So if it is doing this, right? If it is doing this thing, I mean, I liked your strategy of just putting in all zeros or all ones for the first one, because that'll figure out how many there are of each. So actually, this should not be the number correct. This should be the number of ones. And without loss of generality, you can make that number as zeros instead. And then if we say that this is the if you get the number of correct on these, okay, if you're at 1, 1, and you say that there's only one number that's correct, so if you're at 1, 1, and there's only one number that's correct, then you have to change 3 of them. So that could be either all 3 zeros, in which case you're going to jump all the way to the 4. Right, that's the only possibility, because you're not saying that the position matters, or the position doesn't matter for the first little bit. So you can't land anywhere else. It's not possible. So you've got to jump 3 spaces. If there's 2 correct, and you had only 1, 1, then 2 of them have to change. So wait. So that means that it has to be two of the zeros have to become ones again. right? Because it's the only way to make this work. You got to jump 2 spaces. If 3 of them are correct, then you only have to change one number. And it could be either way. Okay, so this one actually could. Could go either way. Okay, so those numbers, the number of ones that are in your particular first guess. Yeah, the number of ones that are in your first guess and the number of correct that you're going to get. Scrap that. The number of correct you get and then the number of spaces you must move is going to sum up to 4 every time. Right? I mean, because that's the number of numbers you have to change. So if you start with, again, list out the number of ones you have in your code. So if you start at 0, there's actually no ambiguity at this point. Right? So you start at 0, and if you have to move 1 space, you go to 1. If you have to move 2 spaces, you go to 2. You go 3 spaces, you go 3. And 4 or 0 correct, you have to go 4 spaces. So you know exactly what, like how far you're moving. And like we have here, there's no ambiguity as far as which way to go. So I think that your intuition about start with all zeros or start with all ones is perfectly acceptable for the first set. Because if you get 1 correct or 3 correct, if you get 3 correct, then you have to move 1 space, but are we going up or down? Right? It's an ambiguity and you don't know which way it's going to go. It's just a different perspective. It's not really all that smart. I was just thinking like, okay, if we do this, because this is another way that I kind of randomly think about stuff too, is, you know, when we were at, if there's only 1 1 in your code and you have to change 2 of your numbers, right? It can't be switching a 1 back to a 0 because you've already got enough zeros for it. Now, if it mattered what position they were in, so it was saying like, oh, well, it is going to tell you, or it's not going to tell you how many are in the correct position, but it counts against you for whatever reason, you know, that would be insane. So let's not do that. So I mean, potentially. So, like, the way that you said it at one point was, let's just assume that all 4 zeros and all 4 ones are incorrect. Yeah, I guess. Um, but if you're always selecting 0, 0, 0, 0 as your starting point, then you'd never know, because you would never actually see all zeros or all ones. Because, again, of our thing up there. Now, if you started with 1, 0, 0, 0 and then ended up with 3 correct, it's equally valid to go either way in terms of like the actual code. So if you went hint 2, okay, I'm going to go to 1, 1, 0, 0 and say 2 of each. And then it said, oh, well, you've only got 2 correct now. Then it's deterministic. Okay, you've got to go back to all 4 of them being 0. You know, the number correct ended up going down, so you've got to go the other way. So So in that particular case, you, you've got 3. Um, but yeah, I'm gonna go with you can definitely get 4 correct on your second guess. Following, start with all 4 being the same. Right? It has to. It can't reselect it. Given that you had to, all 4 zeros, you have 2 correct. Okay, 1, 2. Well, then it has to be 2 of each. So when you do that, then it's going to say, okay, now you've got all 4 correct. If it doesn't say all 4 correct, then something's wrong with the code. Like they're cheating. Right. Yes. And based on what I'm seeing here, they would probably say, all right, so if all 4 were the same for guess 1, and the user can, not necessarily will, but can get 4 correct. No, just on guess 2. Okay, so again, I wouldn't say necessarily that. So like I would say, okay. So it's still going to regenerate within the constraint of H1. So within the constraint of H1 on the one you're saying, where you start at 0, 0, 0, 0, and you get 2. So then you've got to go to 1, 1, 0, 0, or some combination thereof. If you get it, so if it's 1, 1, 0, 0, then it will regenerate, but it has to be within this box. Has to be within the 2 and 2 box. There's no other place for it to go. Yeah. Or they're really messing with you, and it really is this, but you just keep screwing it up. Nope. Again, not likely, but somewhat possible. I mean, like, I don't think it's possible for you all to be incorrect that many number of times. If you've created a little piece of forum, right? If you've created a forum post that was like, all right, no, we need to seriously work this out and start looking at the math behind it, then I think there's probably something there. Chances are. I don't think that it would just be, you guys screwed it up. So I think, again, optimal strategy is going to be guess all four the same. Move 4 minus correct boxes. Alright, so 4 minus the number of correct is going to be the new number of ones. Actually, it's just going to literally be the number of ones in the code. I would ask the devs if this is actually what's going on, and they'll probably be like, no, and then change it. Just to mess with you even more. Optic Sphinx. Hello, good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko, your source for mathematics. If you have any questions, please let me know. Drop it in chat, and I will get to you fairly soon. We're kicking around a problem that has to do something with Mastermind, or a version of Mastermind that Superbrain brought up from Operation Tango. Yeah, I mean, they probably have a Discord, right? So. Okay. Well, thank you. We try to, you know, try to help out and. Yeah, no problem, Super Brain. Just getting another pair of eyes on it almost always, like, gives you a different perspective on it. We try to stay pretty chill in here. Occasionally, I do get rather excited about some piece of math that we're working on. Various people can attest to that. Yeah, because if you're stuck over in one corner, you can't go left. It's I think that this probably has something to do with like all of the like games in Nim that I used to play. So if you know there's an old game that has like 5 or 4. Yeah, I think it's 4, 7, 9, 10. Yeah, okay. Hey. This is just a triangle. This doesn't technically have anything to do with it. So there was an old game of Nim that was stuck on tables in well, specifically in like the Barrel restaurant. Um, there was always this one town in Pennsylvania when we were going from, mid-Atlantic region all the way back up to either New Hampshire or New York, where our families are generally from. Um, so like every single time, right at 12 o'clock, we were pretty much always driving through this town, and it's like, I guess we'll stop at the Cracker Barrel. Um, no offense to Cracker Barrel, it's just yeah. So anyway, we'd go to this restaurant, and they would always have little games in Nim that were on the tables. One of which is a bunch of golf tees that are stuck in a triangular pattern. There we go. That's a triangle. Um, and so there were 10 holes, and 9 of them had golf tees stuck in them. So you could actually choose which one was empty. And the goal was that you would take a particular tee, hop it over a different one, and put it into this hole. At the same time, you would take this one out and eliminate it. So then you have 8 tees that are in place. And then you continue like this until you have no more moves or only one left. If you have only one left, you have won. Yeah, it's a version of solitaire. So if you have one left, you have won. And any, like, there was a little thing at the bottom, like a key, that was like, if you've run out of moves and you have this many, then you are. And, it was like, if you have, if you have like 6 left, you're an ignoramus or something like that. I mean, it was pretty harsh. I don't think that that's even possible. No. You'd have to have 4, 5, 6, I think is the maximum here. So it wasn't you versus somebody else. It was just literally like it's a solitaire game that you play by yourself, and then you try to figure out like what's the optimal arrangement. Yeah. So you're not going against your table mates or whatever. Although they did have they did have the lines, the dots game. So you've got a whole bunch of dots in a rectangular grid. Rectangular. And the goal is that you connect 2 of the lines and your partner connects 2 of the lines that are orthogonal to each other, so no diagonals. And then you go, and then your partner goes. And the goal is to be the last person to close off a square. And when you close it off, you get that square. So, if you went here, then your partner would be able to go down here and claim this one. And so you go through all that, and it's like a, 6x6, 10x10 grid, something like that. So you just go until you're bored, or your food comes, which is really the more likely thing that would happen. So there's all sorts of these are called games of Nim. Grundschule. Grundschule. We call it grade school, but yeah, primary school, it works too. Elementary usually for most of our communities. Which is funny because you have primary school, you have secondary school, which is high school. So for us, that's 9 through 12. And then you have 6, 7, 8, which is just middle school. Because it's between primary and secondary, I guess. Uh, as if they weren't feeling left out enough. Kids at that age, right? High school is your gymnasium or the technique. What's the other one? Yeah, so like college prep, right? Yeah. So generally speaking, in the United States, you've got uh, kindergarten through 5. It's going to be 6 through 8 is middle, or sometimes called junior high. Oop, oh no. Oh no. Turn it off. I hit the button. And then 9 through 12. Yeah. Right. And then you've got all sorts of different places that people can go after that. So you got like job training, tech, technical school. Technical school is often like um, hands-on. It's typically stuff like mechanics. So like somebody who wants to work with cars specifically, like this is very specific training that you're going to get, and stuff that you would normally get on the job, but we can speed that up a little bit. Um, culinary, uh, running a business and stuff like that. Yeah. Anyway. um, that one. Yeah, I still don't do it. as if, as if you couldn't tell. I mean, honestly, it is much easier. What are the differences between Realschule and Hauptschule? So, like, the technical school specifically is like you are going to do specific jobs, and here's how to do that job. So, not many people typically go this route unless they're just like going to leave school and go straight to a job. So we actually had this at our high school. 1 second here. Okay. Why, thank you. Hmm. Okay. So Hauptschule, you've got. So is that your like technical training for people who want to get a job? I could probably look all this up. I have an expert who's here. I mean, somebody who's been a lot closer to it anyway. So we have a technical school that's kind of like up the street from us, and we were going to. Actually, my brother-in-law was potentially going to come down and live with us for a little while. This is like 10 years ago. Mm. No, I mean I understand. Um, so typically after high school, students get an opportunity and they can go to just straight to a job. High school is a general education, very what would be called liberal education. So 9 through 12, well, okay, for us, 9 through 12 is ages um, typically 15 through 18, and sometimes 19 if they're on a little bit of the older side, but it's fine. Most students are most students will turn 15 at some point during their ninth grade year or just after. Most students will turn 18 during their 12th grade year, which is, again, your senior year of high school, um, or, again, the summer after. Most. So, like, my birthday is pretty close to the start of the school year. So I was always one of the first people to turn those ages as I got into each of those grades. So 12th grade, my senior year, I turned 18. Um, again, almost immediately. And then a lot of my friends were later on. So anyway, yeah, after you turn 18 and you finish your high school years, uh, then most companies will want you to go either straight to a job and you just get on the job training, or you can go to a technical school and get like sit down education and also hands-on training on like a vehicle that has, for example, right? If you want to become a mechanic, they'll give you a vehicle with a specific problem, and they'll say like, okay, change the carburetor, or you know, um, first thing in the year, locate the carburetor. And then they find a bunch of cars that have been junked or like abandoned on the side of the road, and they're like, all right, now we've got a Toyota Corolla, go fix it. All right, now we've got a Honda Civic, go fix it. Eventually they get better, like escalating problems with it, and they can figure out all sorts of stuff. Replace the windshield, let's do that. So that's typically what you get for like if you're going to go straight into a job. There's a technical school up the street. Like I said, my brother-in-law was possibly going to live with us for a while way back when, and like, oh, well, we can put you up, and you can go to technical school. We'll take you there every day, and ended up not happening, but oh well. Interesting. All right. So then, apart from this, like if you're going for a degree, then typically you've got a 2 year. which is going to be called associates. 4-year, which is bachelor's. And then typically plus 2 years for master. I mean, this is probably going to be the same. And plus who knows how many megalomorph. I know this is going to hurt you. For a doctorate. Yeah, yeah. Social security number. Yeah. Anyway. So, that's at least pretty standardized. So, you know, you want to have the ability to go anywhere. And so, like, you know, our 4-year institution, you're able to go anywhere in the world and they'll accept your bachelor's as good. You know, that'd be nice. Mm. Yeah, and the other thing was that our curriculums needed to be aligned because, you know, are any of like are any German students going to come to the United States if Germany does not recognize a United States degree, like bachelor's degree? What use would that be? So, you know, they try to standardize the curriculum across the board. I've been actually, because I work here, I work at an associate's granting institution to your college. Some places they're called community college, or sometimes they're called junior college. A lot of places are trying to phase that out as much as they can possibly do. Yeah, they don't want to. A lot of them do not want to use this term, and ours, for instance, is very, very strict about that. And they're like, you do not call this location a junior college. But community college gets a bad reputation up in the Northeast, where I'm from. It basically, like in New Hampshire, community college is almost synonymous with technical school. So, like, a lot of people go to an associate's granting institution for, like, oh, I'm going to get, like, a business degree, you know, an associate's in business, and then I'm going to start my own business, or I'm going to go do something. It's just 2 years. It's kind of a quick thing to get your feet wet, to get you a new perspective, that sort of stuff. And, you know, I've done these requirements. And a lot of people are like, if you go to one of these places, like, you're never going to get your bachelor's, or you're going to have to work 10 times harder to get it. It's not true. I knew plenty of people who went and got their associates and then immediately went to go get their bachelor's, and they only had to do 2 years, you know, whatever other stuff they needed to clean up, do all the higher level education stuff. They'd already done all their general education. They'd already done all the basic stuff for their majors. Like, that was it. So it gets a very bad reputation in New England specifically, but it's actually very good. Like, you know, depending on the institution, there are some places that are complete nonsense. That if you go there, you're just not going to be credible. They can be accredited, but, like, people are going to look at it and go, okay. Why don't you do a remedial class for me, and then we'll figure it out. for us, you have to get, I forget what number. I think it's 60 credits. So, like, that's 2 full years of work. Or, if you come in the summer and the winter, you can do it in, like, 1.5, but it's going to be hard. 18 credits a semester is a possibility. 36 for 1 year, plus 2 summer sessions of, like, you could do it. It'd be pretty rough. Get you another 16. Off of 36 though. It's only 54. So you'd be pretty close. It'd be really hard, but it's possible. Yeah, and that's the other thing, right? If you do AP credits, the advanced placement, our institution grants AP credits from the AP exams, and also if you do CLEP. So the CLEP tests, basically you pay $100, you take an exam, and then it says whether or not you've passed the class just automatically. Whether you have the knowledge to just say, yep, I did it. So I had a 4 on the AP exam out of 5 in Calc 1. Oh, we talked about this last time, but yeah, so I had a 4 out of 5 on the AP exam. I could have gone and just taken the credit, and then I decided that, oh, you're going to give me a place in a special interesting class that's going to like integrate all of the calculus and physics. Okay, I want to do that. And so I rejected the credit. And yeah, I should have taken the credit, gone to Calc 2 immediately, and then only had paid or basically saved myself some time. I could have also then taken, let's see, I was a physics major at the time, so what would I have done instead? Hey, 1,000 cranes. It's going pretty well. We were talking about the educational system in the United States and how it's a little bit different to Germany. Not very much different, but, or at least the secondary system. And earlier we were talking about Superbrain brought up a interesting problem from Operation Tango, which is a game that he and the other players were running up to try and punch a code that is in binary into a keypad. And he said that every single time that they went up to the keypad, it seems like, or at least, empirical evidence suggests that the first 2 times you plug in the code, it's always wrong. And so, like, if we had this awfully mean variation where it is actually wrong both of the first times, what would that look like? So I came up with a possibility here. As far as what the variation could look like, and what it probably more likely is. And he said, well, this one seems more likely also, just from what we've learned from the game. Basically, it's like Mastermind in that if you guess something, it's going to tell you how many are correct. And then if you get all 4 correct, it's going to then tell you how many are in the correct locations. So then it seems like, again, if you always get it wrong on the first 2 guesses, what's going to happen is if you get 0 correct or 4 correct, it's going to basically just re-roll and then give you a different number, 1, 2, or 3, in terms of how many are correct. So 1, 0, 0, 0. I threw up as the first guess for up here, and it says, okay, 3 of them are correct if the correct code is 0110. Now, if my second guess is actually 0110, it has to be wrong. So what it's probably going to do is tell you, oh, sorry, we're gonna re-roll that again. You got it wrong. Yes, I have seen Wordle in a lot of people's Discord servers. There's whole, like... there's just blocks of these colored boxes, and I was like, what is going on? But, yeah. I understand it now. Or at least somewhat. Haven't actually played it myself, but... yeah, so... even if the code was 0110, if my second guess is 0110, it's going to re-roll it and say, oh, nope, that's incorrect. And instead of randomizing it to any code, it's going to be one of the numbers that is in or of the same arrangement. So in this case, it's going to be 2 zeros, 2 ones, but it's not the one I guessed. So, Superbrain gave me some interesting ideas as far as what we could do, and then I came up with this idea that if you actually so his first inclination was to say, okay, just guess all zeros. And I said, if you do that, then it immediately tells you how many are correct, i.e., how many of those are zeros. And so if you have zero ones in your first guess, then one correct is going to tell you that you need to move 3 spaces away from here. So 1, 2, 3, and you've got to have 3 ones in there somewhere. If you have 2 correct, that means that you have to have 2 ones and 2 zeros. If it says 3 are correct, you can only have 1 1. Or you must have 1 1. And then if it's 4 correct, we decided that that's not going to happen on the first or second guess. Or, sorry, it's not going to happen on the first guess. It could happen, and in fact, if you're smart about it, it must happen on the second guess if you start with all zeros. Because, again, if you guess all 4 the same, and then you move a certain number of spaces away, i.e., 4 minus the number of correct things that you get, then that's going to be, it's going to determine which box you fall into. And then again, I said, okay, if you're always wrong on the second guess, then whatever your second guess is, it has to be within the right box, but it's going to re-roll if you guessed correct. So then it's going to stay within that box. So this is like the optimal strategy. But beyond that, we can't really get any better. It's just going to tell you, like, it's just going to tell you how many are in the right place, but then you don't know which ones are in the right place. Ones. And at that point, it becomes a combination problem. So, or permutation problem. So, how many are in the right? No, sorry, combination problem. How many are in the correct position? It's going to be, 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, or 4 choose 4. So, maybe. Because if you do... so let's say it's the worst case scenario, right? So the worst case scenario is that there are 2 and 2, because there are 6 different possibilities for that. 6 different arrangements. So 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 1. right? 6. Okay. So your first guess was 0, 0, 0, 0. That tells you that this is going to be in this list. So there's 1. Your second guess is going to be wrong anyway, so we just guessed that one. So it's wrong. This is going to tell you how many are in the right position. So if you have... Alright, if you have none in the right position, that's super easy. It's just going to be the last one. So that's too easy. It's not going to happen. Okay, so this is going to be 2 in the right position. This is going to be 2 in the right position. This is also going to be 2 in the right position. Is it just all 2s? Yeah. They're all just 2 in the right position. So then if you guess this one, that just swapped the 2 middle ones. So if we guess 0101 and it's not that, then how many are correct? So if it is this one, 0110, it's also going to be 2. 1001 is going to be 2. Oh no. If it's this one, this is going to be 0. Okay. Right, this one's just opposite. So that's too easy. So that's going to be eliminated. So we're going to guess this one. So 0110. If we guess this and it's incorrect, there's only one other possibility, and that's 1001, which again has 0 correct, or 0 in the right positions. So then you know it's that one. But again, it has to be that one anyway because that's the only one left. So if you draw it out. Okay. So then we guess this one is correct. So this was 1, 2, 3, 4 guesses at maximum for this particular thing if you actually play optimally. Right, so you guess 1, guess 2, guess 3, guess... Oh, okay, so yeah, sorry. 4 incorrect guesses. There we go. And then the 5th one has to be correct. And again, same thing. If you end up with any of these other ones, it's just going to be slightly easier because there are fewer possibilities. Yeah. Okay, cool. So I don't think so, because you only have 4 to start with, right? So... Okay, cool. So if you guess 0000, and then we know that it needs to be 3 and 1. Right, now here's the thing, it can only be one or the other. It doesn't matter which one, because that's going to give us the same thing. But if it says 3 are correct, then it needs 1, 1. And if 1 is correct, then it needs 3 1s. So, you know, it's not like we get the list of all 8 of them. Is it literally just n-1 for the number of codes that we started with? So 0001, 0010, 0100, And 1, 0, 0, 0. Is it starch? Is it one of those starch spoons? Or made of food? Alright, so our second guess is this one. And then if it's wrong... Right, this is 2. Are we in this again? This is 2. And this is 2, yeah. So we guess 0, 0, 1, 0. And 0, 0, 1, 0 is still, yeah, it's still 2s. So, because none of them are opposite this time, unlike our 2 and 2, in this case it's not possible. Yeah. So 0, 1, 0, 0. Guess this, and then if this is incorrect, this one is going to end up being still 2 correct, but it's the only one left, so 1, 0, 0, 0. So 1, 2, 3, 4. Oh no, 5 still. Oh, because we... Okay, so up here we eliminated 1 because it was obviously incorrect. Right. Or, sorry, not obviously incorrect. It would be too easy, or we have fewer choices in that particular case. Right? It's deterministic that if you get a 0 back, then you just flop all the numbers and you're done. Or 0 in the right position. Okay, yeah, alright. Apologies. Shouldn't have doubted you. Okay. Yeah, alright. So actually it's not a particular pattern. In this case, it's just 5s each. Right, and literally the same thing happens if you go with, this was 3 correct, this was 2 correct. So same thing happens if you go with 1, just opposite. Yeah, so if you started with 1, 0, 0, 0, and you have 1 correct, then you've got to flip all those. Oh yeah, you have to. Right, that's the only way in which 1 is correct. Or, wait, hang on. Yeah. Get into that in a second, but... No, because if we have a 0 and a 1, then that means you have 2 correct, even if they're in the wrong place. Okay. So with 2 correct... So with 2 correct... So in this particular case, you could never have 1. It just wouldn't allow it. Yeah. So with 2 correct, that's either a 0 and a 1. And then the other 2 are opposite. Or 2 of the zeros are correct. either way. Right, two of them have to change. And then you can't have a 0 and a 1 change because then they would be correct. All right, or is that all we can get for 2? Yeah, right? Oh no, or the... Yeah, right. I keep forgetting where we are. Not literally. If we had 1, and we get 2 correct, and that means we need to move 2 spaces, so then there have to be 3 1s in that particular one. So these are the arrangements of the... Oops. Right, in this case that would be 3 correct, so that's not going to work. So, boop. There have to be 3 1s. Alright, so this is going to short it a bit. It's not too bad. If it's 3 correct, then we have to move 1 space. So 3 of them being correct either. This is wrong. So we have to change that 1 into a 0. Which, again, well, okay. So you're saying it can't be this one because the second guess has to be wrong. Well, okay. So here's the thing. It could be all 0s as long as the person doesn't guess that. Or, again, one of the 0s could be incorrect. So 1, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 0. Because again, we only have to move 1 space, but it doesn't matter which way we go. So if you guess this one, it's just going to shift down here automatically. If you guess this one, right, it's just going to be any of the other 3. Or, again, from the above, from the from the optional version that we looked at here, we said it's going to stay what it is unless we guessed it correctly. So then here, on your first guess, it's going to tell you there are 3 correct. So it could be any one of these 4. If you guess one of these, let's just say the last one, then it could still be 0. But then it would be obvious, because then it would tell you how many are correct. If you guess this one and it's 0s, then it'd be 2 correct. And that's it. If it's any one of these other combinations, it'd be 4 correct, but in a different order. And then you'd have 2 possibilities. And again, those are 2s. So this would be 2 correct, which again feels like it would be, well, it would be obvious to somebody who's actually thinking about it. But any of these, if it's incorrect, any of these would... Oh, no, that's also 2 correct. Or no, sorry. Either. You can't have 4 correct, right? Because we said it can't be that one that you guess. So if you guess this, it must be 2 correct, in which case it's got to be one of these other 3. If you guess one of these, you could get 2 correct, in which case it is obviously going to be 0, 0, 0, 0. Right? It has to be. Or it's going to be 4 correct, and it's going to tell you just order. So then you get 2 possibilities. And that's going to tell you it's going to be 2 in the incorrect location. So then you're back to this same stuff up here. So that's going to be correct there. If you guess, again, one of these other ones, you get 2 correct. So that's 1, 2, 3 guesses along the short path. Or if you're not correct about this, though, you've still, knocked yourself over to this layer. So either way, so if you guess 1001, so 1001 is your third guess, then you're going to get, okay, it's 2 in the incorrect position. And then it's going to say, okay, if 2 of them are just in the incorrect position, then you've got either 1010 or 1100. It doesn't matter which one you pick. And again, here, this is your 4th guess. And then here's your 5th guess is your answer. So again, 5. So 5 steps is still your upper bound. Yeah, it definitely feels like quantum mechanics. I mean, it's not, but it feels like it. This is the Outer Wilds version of quantum mechanics, right? Oh, such a great game. So, Optic Sphinx, he is a character from The Hitchhiker's Guide to the Galaxy, which is one of my absolute favorite books. The entire structure of Marvin's character is around, oh god, everything is awful. So basically, Douglas Adams, the author, created... Originally, he was doing this thing, which was to, like, lambast all technology. And just say, like, I can kind of see where things are headed. And he saw that, like, people were working on AI and, smart computers, things like that. And he was like, oh, God, that'd be depressing. Can you imagine how awful it would be to be a computer that's actually intelligent? And, like, you'd have existential dread. You'd have, like, all this other stuff. So he's saying, like, if you develop a computer that actually thinks like a person... Ghost Pop-Tart. Nice. Thank you for the follow. Welcome in. I am Obi-Wan Pez. This is N Simplex Pachinko, my hopefully your home for all things mathy. We do math streams every Wednesday night and game streams every Friday, and whenever I feel like it otherwise. So. So Douglas Adams originally was looking at, like, what happens if a company were to come up with a computer that actually had a personality, like actual personality. And he thought immediately it would be depressed because it would just be, like, so much smarter than anybody else around. It would have nobody to talk to, like, on the same intellectual level, and it would just, it would feel all the feelings. And so he basically said it is an inevitability that this particular that a smart, intelligent computer would be depressed. So, Ghost Pop Tart, I can help you, or I can try to help you. I'm not actually super great with statistics, but I have done some. So it depends on what level you're talking about. If it's like kind of basic statistics, high school level, yeah, probably can get you there. If it's like college level, kind of depends on where you are in it. And worst case scenario, we can just fumble through. See what happens. I mean, worst case scenario, I've got Google, right? So I have taken several statistics classes. It's just a matter of remembering the particular thing. All right, go for it. So while you're typing it out in chat, um, yeah, so Marvin the Paranoid Android is, while Ghost Pop Tart is typing this out, um, Marvin the Paranoid Android is one of the favored characters among Hitchhiker's Guide fans, just mostly for that reason, that he is an existentially aware and existentially uh, dreaded. I don't know what a good word for that would be, but yes, he has a mountain of existential dread. There are several of his lines, both in the books and in the radio shows, which are, and yes, there are books and radio shows of this. I suggest that you find both because they are amazing, and they are slightly different from each other. Not much, but slightly. If you are in the, well, you are likely in the United States, probably given the time zone. But forgive me if I'm not correct, but Superbrain, I said likely. So forgive me if I am incorrect, but yeah, it is available for like pretty much anyone in Britain, um, and the books are available naturally everywhere. I ended up buying like the, oh no, I ended up buying like the individual books, like the first two, maybe three, that were little paperbacks like this, like, tiny 100, 200 things. Oh yeah, this is fun. Okay, so Ghost Pop Tart. Let's go like this. I'm not going to do that particular problem, no offense, because because of course that would be doing your homework. But let's suggest that we have eh, a place up the street called Frozen Granite, which serves ice cream. They have 12 different flavors. And they have, so with the toppings, for one particular price, let's say, you can pick up to 4 different toppings. And in fact, they don't have to be different. You could just get all 4 of exactly the same thing if you want. And those toppings are, let's see, I don't know, 16 different toppings. So, you got 12 flavors and 4 slots in which to put 16 toppings. And again, you can decide if you want to do like if you want them to be different specifically, or if you just want them to be like all the same. most people would say, oh, well, in the examples that we do, they're probably going to be, if you're going to include a second, a third, a fourth, then they're going to be different. So, for sake of argument. So if we want to know, like, how many different Sundays, or how many different combinations could we make out of all of this stuff? Well, if, for instance, somebody comes in and just doesn't want toppings, that's an option. So it would probably be like a lower price or whatever, but yeah, we'll just assume, like, for one particular price, a person can get any of the 12 flavors, one scoop of any of the 12 flavors or whatever it is, and up to 4 different toppings. So 0 is an option. So if they just select one of the 12 flavors, well, they have 12 different possibilities with nothing else. So then they say, okay, what are the number of combinations of toppings that these people are putting on? So if we look at it, just a lot of chocolate with sprinkles. I think that's called going to the grocery store and getting a tub of frosting. They sell tubs of frosting. All right, so if you don't select any particular toppings, then you have selected one possible combination of toppings. No toppings. Some people get a little caught up on this. All right, so then if we want the number of combinations in which we select one topping. Then what we're going to do is we're going to say, okay, well, we could select any one of the 12 flavors. Then we could select out of one box. Any of those 16 toppings can go in. So, Ghost Pop-Tart and Ghost Pop-Tart only. What does that mean in terms of the like number of combinations that we can get here? What do we do with those two numbers? No pressure. I know that a lot of you just know the answer and you just blurt it out, right? But yeah, so you're going to multiply them. Now the reason for this is really obvious when you draw it. Because what you do is you say, okay, I'm going to select one bowl, right? I have a bowl. And I can do one of 12 flavors. So there's 1, there's 2, there's 3, there's 4, there's 5, 6, 7, 8, 9, 10, 11, 12, right? Any one of those 12 leads to a new node. And I mean, I could have done this actually properly out in a much better format. I could have done it with a much smaller number. I'm just thinking about the actual frozen granite store up the street. Anybody who's in the US knows exactly what I'm talking about. All right, so here's one bowl. Here are the 12 flavors. Oops. That are going all the way around. And then on each of them, I can select one of 16 toppings. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's one. Right? So any one of those 16 toppings. Now you look at it and how many nodes are there, right? There are 16 nodes at the end of each of the 12 nodes that we had for the flavors. So yeah, this is going to be multiplication because we're going to say, all right, well, the next one also gets 16. And remember, multiplication is just repeated addition. So we're going to add the 16 toppings onto every single possible flavor. So let's shortcut it, right? We're going to multiply this thing and make it much easier for ourselves. All right, so then the same thing's going to happen when we look at the number of combinations in which we select two toppings. Well, we still have 12 for the number of flavors. We're still multiplying by 16, which is the number of different toppings we can get for the first topping. And again, since the toppings have to be different, now how many toppings will there be for the second topping? And that's going to mean, in our diagram, each of those nodes is now going to get however many new toppings. So we have to multiply again. Okay, so anyway. So the next one is going to be out of two toppings that are selected, the next one has to be one of the other 15. All right, and then if we do, again, number of combinations, in which we select three toppings, then we're going to do 12 by 16 by 15 by 14, because now again, we have to have a different topping than the ones we had before. So this is going to be 14 more nodes off of each of those 15 that came off of each of the 16 that came off of each of the 12. So this spider web is going insanely large. It's just going to be immensely humongous, and we're never going to be able to draw this, right? A computer could draw it fairly easily. And then lastly, number of combinations of making something with four toppings ends up being, you guessed it, 12 by 16 by 15 by 14 by 13. So redo this one here. So by 13. Then, if we get all these different combinations, as long as we consider those to be different ice creams, right? So just ice cream with one topping, ice cream with two toppings, ice cream with three toppings, and ice cream with four toppings. As long as we consider every single combination of these to be different, we can then take all of these things and do what with them? My day's been all right. Thank you for asking. Spent most of my morning kind of half asleep, so spouse came into the room, found me napping at my computer when I was trying to write. So that didn't go well. But to be fair, I was trying to watch a Twitch stream, so like that wasn't going to help with me with writing, unfortunately. Probably have to shut everything off and actually focus. Yeah. So it can be used for this problem, but you don't need to. Mostly because this is a small number of boxes. It's fairly easy to do. And in fact, the problem that you are working on, you don't need to at all. So the thing that's happening with the problem that you are working on is that you're selecting one thing from each category. And actually, we did talk about this quite a long time earlier in the stream. This is a particular mathematical function called choose. So what's happening is, in this particular case, we're saying that we want to choose, we have 12 different flavors of ice cream, and we're going to choose one. There are 12 flavors, choose one. Now for us, the actual definition of this is not too bad, and we'll get into it in a second here, but um, all of the combinations that you had up there in your version were all some number choose one, which ends up being just the number that you had there. Because if you're going to choose one of them, then it's going to end up being one possible combination. Or, sorry, wow. It's going to be that many possible combinations. So in the case of 12 choose one, we have 12 possible combinations. If, for instance, we did no, that's not technically correct. Okay, interesting. Sorry, I'm doing something in my head. If we wanted to choose, of the 12 flavors, choose two, 12 choose two actually only looks at what would happen if they are distinct from each other. So, like, you can't choose the same flavor twice. So, like, you wouldn't be able to choose the same toppings twice, for example. And we could make a much larger problem out of this, but same idea happens here. So what's happening is we're saying, okay, 12 choose one is going to be the flavors. And then we're going to multiply by the number of toppings. So in the first case, we actually did 16 choose 0. We didn't want to choose any toppings, right? Now, if I choose 0 toppings, this means that we have one possible combination of toppings. There aren't any. It's a little weird, but it sort of makes sense. Okay, and then we said, okay, the second one is going to be 12 choose 1 for the flavors times 16 choose 1 for the toppings. Again, 16 choose 1 is 16, and that's where we get this one from. Plus 12 choose 1 times 16 choose 2, because we wanted to know what would happen if you choose 2 toppings. And again, they have to be different. Plus 12 choose 1 for the flavors times 16 choose 3 for the toppings, plus 12 choose 1 for the flavors times 16 choose 4 for the toppings. So like this is the long form of everything. You don't want to do this when you're actually writing stuff out. But in this case, it kind of helps organize like how does this all work. So the choose number that we actually use here is often written as NCR, which is N is going to be the size of your pool, and R is going to be the number selected. Size of the pool can also be called the number of selected from. So NCR is defined as n factorial, which, again, we'll talk about what that means in a second, divided by r factorial n minus r factorial. Now again, what does that all mean? So, n factorial is going to be the number of ways to arrange n objects. Right, without respect to anything else, they are different objects from each other. So actually n distinct objects. Have to throw that caveat in there. So, you've got, for instance, the 16 toppings that are there. How many different ways could you arrange all of the toppings on the counter if they were all just in a line? That would be 16 factorial. So, all the different possible ways of shuffling them around, that's going to get you a 16 factorial. So, the number of what are yes. So the number of permutations of the toppings containers would be 16 factorial. Right? You've got 16 bins. How many different ways could you arrange them on the counter? Okay, now there's also a lot of other stuff going on in here, right? R is going to be the number of selected things. So what is this R here in the bottom doing? Well, this is saying that in this particular case, we don't actually care what order the selected things are being selected in, right? If they're toppings on an ice cream cone or in your bowl or whatever, you don't really care what order you put them on, probably. Or at least you're not going to care about it, like, you know, as soon as you mix it in. So r factorial is the number of ways to arrange the selected objects. So again, in our example that we had before, number of different ways or number of different orders to put on the toppings. So in the case of 4 toppings, it's going to be 4 factorial ways. And I should probably explain what factorial actually means. So, right, so n factorial is going to be defined as n times n minus 1 times n minus 2 times every single number all the way down to, oops, I don't need that, times 3 times 2 times 1. So all whole numbers that are getting multiplied together all the way down from n, whatever your first n was, all the way down to 1. So in the case of 16 factorial, this is going to be equal to 16 times 15 times 14 times all the way down to 3 times 2 times 1. Every single number in between, 16 all the way down to 1. Now that is a large number. Large. Yeah. So I don't even have I don't have an exact number for it, at least not with a TI calculator. This is going to be 20. Right, the number of ways that the staff could arrange 16 toppings containers on the counter is 20 trillion 922 billion 789,890, which I'm going to question that because I don't actually have the... Well, actually, it has to be 90, right? Because there's a 10 in there. Provided it's not just rounding it. Right, the last digit has to be a 0. Wait, if the last digit's a 0, it has to... Yeah, okay. Has to be that. Hang on. Million, billion. Nope, I screwed up. That's bigger than that. Right, so this actually doesn't have to be 90. I have a 9, and then I have 1, comma, 1, 2, 3 places that I don't know what they are, and probably Wolfram Alpha can go that far, but... So 16 factorial. 789. 888. Yep. So I was right in one of my ramblings there, because that it did round it. 8 8 0 0 0. So 20 trillion 922 billion 789 million 888,000. So that's a lot. Almost 21 trillion different ways to arrange those things on the counter. Now again, we don't really care in what order the staff puts them on our ice cream, so we're going to say, okay, that's 4 factorial that we don't care about. So this is going to be equal to 4 times 3 times 2 times 1. Nice and easy. 6 by 4 or 12 by 2, however you want to multiply it, it's going to get you 24. Now the other piece here is the n minus r factorial. So this is going to be the number of ways to arrange the non-selected objects. So in this particular case, the number of different arrangements of the toppings not used. So, like, who cares about them, right? Because we're not using them. So they're not going on our ice cream. So we can take those out and get rid of them because it's not going to matter. N minus r in this particular case is 16 minus 4 parentheses factorial is 12 factorial, which is 12 by 11 by 10 by etc. all the way down to 3 by 2 by 1. Okay, so then, oops, 16, turn that to 12, and we get a bit smaller of a number, 479,001,600. Okay, so NCR is telling us that we're going to take our 16 factorial and divide it by both 4 factorial and 12 factorial. Because we don't care about the arrangements of the toppings that are used and also not the toppings that are not used. We don't care. But we need to know how many of them there are. So that balances the 16 factorial from the top. Right? The number of combinations of everything versus the number of combinations that are actually being used, oops, this one, and the ones that are not used, this one. All right, so this is going to be 20,922,789,000, nope, 1,888,000 divided by 4 factorial was 24 by 479,001,600. So that is multiplication here. And if we do this properly, then we end up with a 16 factorial divided by parentheses. And I'm going to remind you, definitely put parentheses in there. Okay, so I could have actually typed this into Wolfram Alpha as 16 choose 4, which would have been much smarter. Divided by 4 factorial times 12 factorial. So the number of different Sundays that we had up top there, which were all of these things multiplied together, and then all of those oh, no, sorry, this is just one of them. Right, this is just the last one. So the ones with 4 toppings only. So let's change that. Let's go like this. The ones with 4 toppings only ended up being 1 times 16 choose 4 is going to be 1,820. So if you want, you should be able to, oops, that's not 1, that's a 12. Apologies. All right, and I'll show you why in a second. Okay, 1,820 is going to be the number of combinations of toppings that you can get. Again, 4 toppings out of the 16. Okay. So then this goes back and can propagate through the rest of them. 16 choose 3, 16 choose 2, 16 choose 1 is going to get you all these different numbers. And again, you can manually do them out by just doing 16 times 15 times 14, 16 times 15, and 16. And then multiplying all those results individually by 12 from the 12 choose 1. 12 times, 12 times, 12 times, and then add them all up at the end. So 16 choose 0, if we choose 0 toppings, there's one possible arrangement of that. And again, 12 is going to be the number of flavors that you can get for this. I'm going to fill this in. Optic Sphinx, right? Sorry. Optic Sphinx. Go ahead. All right, so 16 choose 1 is 16. 16 choose 2 is 16 times 15, which is going to be 256 minus 16. It's going to be 240. And 16 choose 3, I'm not going to be able to do that one in my head that easily. 24 by 14. No. 14 is 3,360. That doesn't seem right. Hang on. Yeah, this is one that gets people tripped up a lot, due to the fact mostly that the less than word is terrible in English. In almost every other language, they're okay with using something that implies how to actually do it correctly. But English goes this sort of, well, if I say the word, it's going to be obvious to you, but in a backwards manner. Oh, is that why? Yeah, okay. 16 choose 2 is not 240. That's my problem. I forgot. There's one other thing that's going to happen in there. When we're just multiplying these numbers, let's see. Nuts. Lost my train of thought. I got a bad feeling about this. I need to have a think about this one. The choose. Because again, this is not actually going to work as a choose. But we'll come back to it. Give me a few minutes here. So, Object Sphinx. If you've got... oops. Right, very similar, naturally. If you're looking at 8 more than 3 times a number is 20, then where do you want to start with this? Hmm. So where I would say probably you want to start is going to be here. That is an easy and direct translation from English to mathematics. All right, so the number, or the number, the word is telling us that this is an, again, this is one of those things where, like, normally I avoid using obvious words to try to get you to say them, but again, we got a time delay, it makes it awkward. All right, when you say is, this is what's called an equivalence relation. So you're saying that when something is something else, then these things have to be equal to each other. All right, in this particular equivalence relation, this is how this works. And all the stuff on the left can end up on the left over here, and all the stuff on the right can end up on the right over here. That one's nice and easy at least. It equals 20. All right, then you got to look at 8 more than 3 times a number. Well, for this actually goes with order of operations. And again, it's sort of like learning how English translates to the order of operations. So first of all, a number. Right? There's your variable. So let this be your y, your x, your n, your p, your a, whatever you want it to be, variable. And just to be difficult, I'm going to make it p. All right, then what do we do to that number? So if we are going to start with p, our variable, what do we do to it? So the next thing that's here is that immediately attached to it is going to be 3 times. Or the phrase is 3 times a number. Right? So this is the larger phrase. 3 times a number. All right. Then we look a little bit larger than that. What's the next stage? Well, it's 8 more than 3 times a number. Right? So this happens at the last stage. It doesn't necessarily have to do with like the words, but like the order in which the words come. 8 more than this amount means that we're going to take this amount and we are going to add 8 to it. Now, if you want to start with parentheses and say like, okay, we've got a number which is p. We've got 3 times a number, which is 3p, and then 8 more than that thing is going to be add 8 to it. Now, it's a little weird and awkward that here we put 8 more than first, but usually we tack it on at the end. Now, it doesn't really matter. This could have been 8 plus 3p. Equals 20. That's perfectly valid. Let me put that over a little bit, but really. Could just as easily have been 8 plus 3p. But there's a problem, and that is when you go with the other way, right? When you say 8 less than. Right? Exact same thing, just change one word. Less instead of more. All right, what's that going to do for us? Well, that's going to say, again, we're going to start from the inside. We've got the equivalence relation is, so equals 20. On the other side, we have a number, which, again, we're just going to let it be p. 3 times that number is just going to be 3 times p. All right, and then we have like your parentheses or whatever, and then 8 less than that amount. So what are we doing? Well, this is a modifier on 3p. So we're taking 3p as like our base value, and then we have to make it lower by 8. So make it lower by 8 means that we need to take this thing and subtract 8 from it. Because again, less than is modifying 3 times a number. Almost every student that I know wants to start with 8 less than is minus. 3 times a number is 3p. Is equal to 20. But the problem is that this is not what this says. At least not in English, because English is a weird language. And believe me, I have all sorts of problems with the way things are said in English versus every other language in the entire world, or just about. Well, and then there's the worst thing that can happen, which I really hope that they don't do this to you, but I've seen it before, in various places. 8 less 5. So what this means is that we are starting, it's not less than a certain number or whatever. It says that in this case, we want to start with 8 as our base value and then less 5. So subtract 5 out. I think that this comes from the older English word for leasing. A lessor or a lessee is somebody who leases something, and so it's kind of like if you are going to start with 8 houses and you are going to lease out 5, then the way you would calculate that is 8 less 5, because you are going to less out 5. It's terrible, but I think that's basically the root of where it all comes from. That's just me pontificating. It's not necessarily true, but it seems to have a connection there and make some sort of sense-ish. But at any rate, I am not necessarily correct on this. Just letting y'all know. Okay, no problem. All right, so next question is, why are these not the same as those? That's not what I want. That one. All right, so all right, I seem to have painted myself into a corner here. So if anybody else has significant education in statistics, let me know, or combinatorics, really. Let me know, because I just messed something up and I can't figure out why these are not the same thing. Which is somewhat silly, but again, like I said, this is very silly. It worked for choose 1 and choose 0, which makes sense. And then as soon as I do choose 2, it breaks down because I just completely... It's like here I'm doing the permutations. Yes, okay. So in this particular case, I'm doing permutations. So it doesn't actually matter what order I put them in, right? So the two toppings could have been topping 1 and then topping 2, or topping 2 then topping 1. Because again, the order doesn't matter. So that's what the problem is here. It's not just 16 times 15 because they're of the same category. I need to then also divide by 2, or 2 factorial, which is 2. Number of ways to order 2 toppings. Okay, so then 16, 15, 14 would have to be divided by 3 factorial, which is 6. Because now we need to look at, this is the number of ways to order 3 toppings. And then this one has to be divided by 4 factorial for the same reason. Okay, so these numbers now match. So we get the 16, the 16 choose 2 is 120, not 240. Nope. 120. All right, 12. This is 16 choose 3. It's 560. And then 1820 is 16 choose 4. So again, 1820 came from 16 factorial divided by our 4 factorial, 12 factorial. And again, all of that is in the denominator. This one here came from 16 factorial divided by 3 factorial, 13 factorial. 120 came from 16 factorial over 2 factorial, 14 factorial, etc. All right, so once we add all of these things up, this gets us the total number of possible combinations of ice cream and up to 4 toppings, including 0 toppings as an option. So this is going to be 12 plus, you know what, 12 parentheses, 1 plus 16 plus 120 plus 560 plus 1820. Again, all of that is being multiplied by 12. Gets us a total for this particular thing of 30,204 combinations. All right. So, Ghost Pop Chart, if you're still here, how's that look? I know your problem is a little bit different, but again, it's almost the same. the main thing is that this one that we did is actually a little more generalized. So this is a little more powerful. The main difference is that the one you're doing, every single choose is always going to be choose 1. So you had a number of donuts, a number of frosting, and a number of like sprinkles or whatever there was. I could just literally scroll up. Oh, okay. So it's not even that. Cupcakes, donuts, muffins, donut holes, and pandule. So you got 5 different things, and you want to choose one of every type. How many different things could you make? How many different things could you collect? So again, same thing here. You're saying, oh, well, this is going to be, the first one ends up being 11, choose 1. But also, then we want to pick 12, choose 1. And also 4, choose 1, etc. All right, so when you do all of those individual types, remember that choose 1 ends up just being this 11 factorial divided by the number of choices is going to be 1 factorial. Well, that's that number multiplied by every number down to 1. It is 1, so it's just 1, right? The other way to think about it is, how many different ways could you arrange one object? There you go. Right? That's the number of ways to arrange one object. It's 1. All right. Misakide, got any problems? Questions? Interesting curiosities? All right, and then that was that minus that, so it's 10 factorial there. The fun thing about factorials is that here, when you've got 11 factorial, you've got 11 times 10 times 9 times 8 all the way down to 2 times 1. And then on the bottom, you've got this 1 from the 1. And 10 factorial is 10 times 9 times 8 times all the way down to 2 times 1. And all of it is multiplication and division. So we could just say, all right, well, this thing gets divided out by this thing. So it's 11. All right, so 11 choose 1 is equal to 11. And that would go in that position, etc. If anybody else has any more questions, please let me know. Drop them in the chat, and I will happily give you something to think about. And welcome to anybody who's lurking. If you're just hanging out, happy to have you. I'd say it's been a productive night. If anybody does have any more questions, let me know. Other than that, I think we're going to start. Yep, go ahead. Nope, go ahead. Goodness. Okay. Integral from 0 to 1. Separate or same? Or, sorry. Are those different, or is that a correction? Okay, those are different. Okay. So sine squared of... You really want to keep me around tonight. 1 minus h squared all over 2 dh. Okay, integral from 0 to 1 of hyperbolic sine squared, square root 1 minus h squared over 2 dh. Welp. Say maybe your best bet here is going to be power reduction formula. So let's see. Sine squared theta is equal to 1 minus cosine of 2 theta all over 2. So integral of 1 minus cosine of just the square root of 1 minus h squared. And I'll kick 1/2 outside. dh. Okay. This might be a stupid idea, but let's try this. So we're going to go with, that's what I excel at. So let's do trig sub here. So if we let h be the cosine of theta, dh is going to be negative sine of theta, d theta. It's going to be 1/2 integral from 0 to 1 of 1 minus cosine of square root of 1 minus cosine squared theta times negative sine theta d theta. No, I picked wrong, didn't I? Oh no, either way, it's going to come out to be the opposite one. Ugh. Or rather, this one is going to end up being the same as this one no matter what I do. Alright, cool. integral from 0 to 1 of 1 plus, oops, 1 plus cosine of square root 1 minus, nope, 1 minus cosine squared is going to be the sine squared of theta times sine theta d theta oops, this is h. Plus. So this is going to be interesting. This is going to be a cosine of a sine of theta times the sine of theta d theta. But that's not going to be pretty nice here. I mean, if it were nice, you wouldn't be asking me about it probably, but... Is this from any particular class? Hmm. Alright, the derivative of something that looks like that. Oops. Cosine of a sine. It's going to be equal to the negative sine of the sine of theta times the cosine of theta. d theta of, let's do this. What is the derivative of a sine of theta? So it's going to be a cosine of theta. Nope, not cosine of theta. Cosine of the sine of theta multiplied by the derivative of the inside as a cosine of theta. So here we've got mixed. This is not good. Well, the d theta in all cases. Actually, the d theta is already here. Never mind. Differential equations and all that. Okay. So it looks like we don't have a nice answer for this. At least, again, none that I can see immediately. Interesting thing also, this should technically be the absolute value of the sine of theta. However, cosine is being acted on. If h is cosine, then h is going from 0 to 1, and h is going from 0 to 1. Then the integral is going to be on the... Nope. Integral is going to be on theta, going from pi over 2, where the cosine is going to be 0, so the h value is 0, up to where the h value is 1, which is when h is 0. Sorry. Wait, no. Theta. Theta is 0. So this is like a backwards integral. Yeah, I don't have a nice answer to that one. Now, being curious, I will actually just look up the answer because sine squared of square root 1 minus h squared over 2 dh. No result found in terms of standard mathematical functions, which is what we were looking at in the first place. That's not what I wanted. Come on now. Okay. So numerically, you're not going to like this, but numerically, this gets a value of about 0.155. I mean, you probably looked this up too, so it's not necessarily helpful. If we pop this in, this is exactly equal to 0.1. Oh no, it isn't. It's approximate. Okay. Zero 0.1781 and a bunch more numbers. All right, so how does this work? If it's hyperbolic sine, we could go one of two crazy ways, one of which is actually do it out and try to figure out what e to the whatever is going to be for this stuff, and I ruined your game. Were you trying to see if they were going to be exactly the same? Alright, so the sine, hyperbolic sine is going to be e to the x minus e to the negative x over 2. And if we square that... No, I mean, that's... So e to the 2x... So it's minus 2 plus e to the negative 2x all over 4. So then replace x with these nasty things. 1/4. It's going to be e to the square root of 1 minus h squared all over 2 plus, oh, that's, never mind, that plus e to the negative of the same square root minus 2 dh. Yeah, and then again we're stuck with the same problem. Where we can trade h for something to do like trig sub, but then it's e2 a sine value. So that's going to be kind of gross. Anyway. Well, thank you for the diversion anyway. All right. I think that will about do it. So we will look up who else is on tonight. I mean, I got the numbers. Numerical analysis in terms of, yeah. So I can get the numerical analysis. Did you like? I don't know. What do you mean? Hmm. Oh, do you have like gamma functions and stuff? Yeah, you can go for it. Let's see, who else we got?